All right, so this set of videos is going to focus on when the objects are now connected in some way. So really there's two ways that this happens, is that they're either going to be physically touching or they're going to be connected by a string going over a pulley. Okay, so connection object problems in physics involve two objects that are connected by it should be that. So this should be string, right? So connected by a string, that goes away. That usually passes over a pulley. And I apologize for that. It took me a second there. Okay. So what we do is we assume that the pulley is ideal at this point in time, which means that it is massless and frictionless. So there's going to be no contribution of the pulley's mass or friction. When we start taking this into consideration, we're looking at torques, which falls in the area of rotation. Okay, so we're not there yet. Okay. Now, when doing connected object problems, okay, you'll need to do multiple free body diagrams. Okay, multiple meaning two or more. Okay, and then here's the key about connected object problems. So when you set your coordinate axes, it must pass through the pulley. So one of the problems is what is called a modified Atwood machine. And so basically it's a block on a table with a hanging block. So for the block on the table, I can keep my coordinate system as convention. Okay, it's a positive x to the right, positive y up. But what has to happen is my coordinate system has to travel down the string, okay, and do what the pulley does. So it's got to do what the string will do. Okay, so imagine that the coordinate system was part of the string. Okay, and when I let this system go, it's going to travel down the string, and what's going to end up happening is your positive x is going to point down, and your positive y is going to point to the right. Okay, now it's going to be weird. Like math teachers don't like this. So like you can't change the coordinate system, but in physics we change the coordinate system to make our lives easier. Case in point, inclined planes. Okay, from the last videos. All right, and so now there are generally three types of connected object problems, and they all fall under the heading of an Atwood machine. Okay, Atwood machine is a machine invented by George Atwood, who decided that these showed mechanics very well. Okay, but basically what an Atwood machine is: two objects connected by a string, and that string passes over a pulley. Okay, and so when we talk about a modified Atwood machine, it's on a table. An Atwood machine is just simply hanging on its own. Right. So here's the question. First example: an Atwood machine. Two masses of big M and little m are connected by a massless string, and that string is passed over an ideal pulley. A, what is the acceleration of mass 1? B, what is the tension in the string? And then report your answers in big M, little m, g, and other constant values. Because this is typically what they ask on the AP test. And I think I got this question from an old AP test or AP resource. Okay, so here's our physical picture, all right? So we have little m, we have big M, okay? And what will happen is big M is the one that's going to accelerate in the positive direction, which means if I kind of follow through with that idea that I have to my positive sign has to go with my coordinate system has to go with my pulley, okay, right? And this is going to point in the positive points in the direction of the motion, okay? Now it says, what is acceleration of mass 1? Because it's going to be the entire system. So the system is going to accelerate at the same rate, okay? So I have to do two free body diagrams because I have two objects. The thing is, they're going to have the same free body diagram. Okay, so I'm going to have tension, and then I'm going to have weight. I'm going to say FG1. Okay, so this is block 1. This is big M, right? Now I have where big M, the positive, is down. Okay, now I have little m, which has the same free body diagram. It's FG2, right? But remember, this one's going to have a positive up. Okay, and now so there's my draw step. Now I'm going to sum the forces for each object. So it's going to be FG1 minus T equals big M times A. And then over here, I'm going to have T minus FG2 equals little m A. Okay. One thing I want you to notice, I didn't put a subscript with the T or the A, right? So for the tension or the acceleration, because the tension or in rope 1 versus rope 2 is going to be the same. And the acceleration of block capital M versus little m is going to be the same. Okay? So now you can apply like math techniques here, right? And we know that FG is mg, so big mg, I'm going to say minus t equals big ma, right? And then I've got t minus little mg equals little ma, right? So guys, now I'm gonna do some systems of equations. So I'm going to rearrange the first equation I wrote over there, with the big one. I'm going to put the little one on top. Okay, and I'm going to rearrange the other one to put the t in front. Okay, and so now I can do elimination by adding down. So I got big M times little g minus, oh, wrong one. I want to erase, not pan. All right, so big M little g minus little mg equals big M A plus little m A, right? And I can factor out a g here, so mg, I'm going to factor out a g, so it's going to be g times big M minus little m. Factor out an a here, because that's what I'm looking for, m, big M. All right, I'm going to divide both sides by big M plus m. Big M plus little m, and here's my acceleration. Acceleration equals g times big M minus m over big M plus m. And I'll tell you this is the signature of Atwood machine. At some point in time, you're going to divide by total mass. Okay, now I don't know if I left myself enough room to find the tension. Okay, so now I'm going to take that and plug it in, okay, into one of my other equations, right? And so let me do, so I'm going to say T equals little mg plus little ma. I'm going to say T equals little mg plus m times g big M minus m over big M plus little m, okay? And I don't know if there's anything, right, so I can factor out an mg. So T would equal mg times 1 plus big M minus little m over m plus little m. There, so there's my tension. Okay, so here's my acceleration, which is part A. Then here's my tension in the string, which is part B. I could have done it for the other equation too, and it just gives me just a different look to the equation. Okay, but you're gonna, if whatever numbers you plug in now would give you the same answer. Okay, and I'm gonna do a separate video for a modified Atwood machine, and then I'm gonna do another video when we put it on an incline. Okay, just give you a little preview of some of the things that are coming up, and then we'll do when they're touching or separated by a string on a horizontal surface.